Welcome to This Explainer. Today, we're tracking a truly mind-bending journey. We're going to look at how a famously sarcastic thought experiment from way back in 1935, one that gave us literally the most famous hypothetical feline in history, has completely transformed. We'll explore how this massive philosophical headache didn't just stay a quirky pop culture meme, but actually evolved into the literal foundation of a multi-billion-dollar technological arms race culminating right now in the year 2025. Okay, let's just dive right into this and immediately debunk the biggest myth out there. When you hear about Schrödinger's cat, the popular everyday idea is that Erwin Schrödinger literally believed a cat could be alive and dead at the exact same time. Well, he didn't. He actually invented this incredibly bizarre scenario to show exactly how absurd the leading physics theories of his day were. He wasn't endorsing the idea of a half-dead, half-alive cat. Actually, scratch that. He was heavily critiquing it. You know, what's so fascinating is that this famous thought experiment was forged as a weapon. Back in 1935, right in the thick of a really bitter scientific debate, it was created to mock the so-called Copenhagen interpretation of quantum mechanics. This was the theory championed by his major rivals, folks like Niels Bohr and Werner Heisenberg. Schrödinger, who was allied with Albert Einstein on this, found the philosophical implications of their math just appalling. So he wanted a crystal clear, macroscopic example to show the world exactly why he thought their whole theory was incomplete. All right, let's hit section 1, the famous feline myth. Picture this kind of lethal Rube Goldberg machine. You place a cat in a completely sealed, opaque steel box. Inside with the cat, you've got a radioactive atom that has an exact 50-50 chance of decaying within an hour. Now, if it decays, a Geiger counter detects it, drops a hammer, smashes a vial of deadly hydrocyanic acid, and, well, the cat dies. If it doesn't decay, the cat lives. But here is the massive quantum catch. Before you open that box, the atom exists in a superposition, meaning it has both decayed and not decayed. Because of this, the atom state forces the entire box, the detector, the hammer, the poison, and yes, even the cat, into one giant entangled quantum state. It's like a single interconnected puzzle. Which brings us to section 2, the quantum measurement problem. So this poor hypothetical cat exposes the absolute core crisis in physics. When exactly does a fuzzy quantum possibility become a concrete physical reality? And you have to remember, superposition isn't just us being ignorant of the cat's true state. No, rigorous interference experiments prove the particle genuinely exists in a literal combination of mutually exclusive outcomes simultaneously. It's wild, but the math demands it. And that thought experiment reveals just a massive, massive puzzle. The mathematical formalism of quantum mechanics treats measuring devices, like that Geiger counter or even a human observer, as purely classical objects. But it never actually defines where the microscopic quantum world ends and the macroscopic classical world begins. This leaves us with these huge dilemmas. How do we actually get a definite outcome? Why does the system choose the alive or dead basis anyway? And seriously, where exactly is that quantum classical cut?
Let's look at section 3, many worlds and decoherence.
To solve this paradox, physicists have dreamed up, well, an absolute menagerie of wild interpretations. Because while the math works perfectly, and it really does, no one can quite agree on what it actually means for reality. On one hand, you have Niels Bohr's Copenhagen view, which is kind of the classic textbook answer, requiring this sudden, unexplainable collapse of the wave function the exact moment you look inside the box. Pitted directly against it is Hugh Everett's many worlds theory, where there is no collapse. Instead, the act of observation literally causes reality to fracture. Both the alive cat and the dead cat persist, but they exist in completely separate parallel universes that can never interact again. But, you know, how do physicists practically deal with this today? Well, most modern physicists rely on a process called decoherence to explain away the paradox. Think of the environment itself, the air molecules in the box, stray photons, ambient heat, as a continuous measuring device. They're constantly bumping into the cat, extracting little bits of information, and irreversibly entangling with it. So the environment is essentially constantly looking at the cat, effectively destroying the superposition before we even get a chance to open the box. To really wrap your head around the sheer scale of decoherence, consider this incredibly tiny time frame. 10 to the power of negative 23 seconds. It takes just a fraction of a fraction of a fraction of a second for something as small as a single grain of sand to lose its quantum state due to environmental interaction. And that is exactly why we never see macroscopic objects, like cats, walking down the street in a superposition. The environment just instantly forces them into a classical, everyday state. Moving on to section 4, The cat qubit revolution. Let's fast forward to the year 2025 and see how this builds from a purely philosophical headache into the absolute foundation of a cutthroat, real-world technological arms race. In the first quarter of 2025, tech giants like Amazon, Google, and Microsoft unveiled fundamentally new quantum chips, and they're all desperately trying to solve the core problem of quantum fragility. The exact same fragility and decoherence that Schrödinger hit the nail on the head about back in 1935. A modern quantum bit, or qubit, is essentially a miniature Schrödinger's cat, existing in a superposition of 0 and 1. And keeping that super delicate state stable, that's easily the hardest engineering challenge in the world right now. What's absolutely wild here is Amazon's Ocelot chip. They are literally using something called cat qubits. These are macroscopic superpositions of distinct classical-like states inside microwave cavities. And by using these cat states, they inherently protect the system against what are known as bit flip errors. This is a real game changer. It reduces the error correction resource overhead by up to 90% compared to standard methods. They're achieving bit flip retention times approaching 1 full second. Now, 1 second might not sound like much, but in the quantum computing world, that's an eternity. They are literally using Schrödinger's paradox to physically build a better computer. But wait, the tech leaps definitely don't stop there. In April 2025, researchers at the University of Innsbruck in Austria announced a massive breakthrough. They successfully created what they're calling hot Schrödinger cat states. Up until this point, everybody basically assumed that to maintain these delicate cat states, you absolutely had to cool your hardware down to near absolute zero, just to prevent ambient thermal noise from destroying the superposition. But by pushing the operating temperature to 1.8 Kelvin, which sure is still cold, but it's actually 60 times hotter than typical quantum computing conditions, the Innsbruck team proved that you can maintain superpositions in environments previously thought to be way too warm and noisy. And why does this matter? Well, operating at these hotter temperatures dramatically reduces the immense cost, power draw, and sheer complexity of the refrigeration systems needed for future quantum hardware. It suddenly brings practical quantum computing so much closer to our everyday reality. Finally, let's wrap up with Section 5, an unfinished quantum mystery. Yet, even with all this, despite generating a multi-billion-dollar quantum industry and all these incredible, mind-blowing engineering feats, the philosophical weight of Schrödinger's original 1935 paper remains super heavy. We've mapped the math beautifully and we've engineered the prototypes, but the actual nature of reality, that remains fiercely debated. I mean, which interpretation is definitively correct? Is the wave function a real physical thing, or is it just a mathematical representation of human knowledge? And how does any of this connect to Einstein's gravity? Physicists like Arkady Plotnitsky in 2024 have even been proposing entirely new frameworks, like reality without realism, basically trying to accept that quantum mechanics describes something fundamentally real, but it can just never be described in classical common sense terms. The cat just refuses to be solved. Almost a full century later, it continues to force us to ask the absolute deepest questions imaginable. It leaves us with this ultimate provocative thought to take away today. If decoherence means the environment is constantly observing the cat, forcing it into a classical reality, and you are standing there observing that environment, then in a quantum universe built entirely on observation in entangled states, who is observing you? Thank you so much for joining me on this explainer. Stay curious, keep learning, and I'll catch you in the next one.